So now let's consider the high frequency case. So when omega is much bigger than omega n, then we write omega over omega n is much, much bigger than 1. And so if we look at this term here, then the dominant part is this thing here, minus omega over omega n squared. So at high frequencies, we have that g of j omega equals 1 over m omega n squared times 1 over minus omega over omega n squared. And so when we multiply all that stuff out, these two omega n squareds cancel. We get minus 1 over m omega squared, okay? Which is, again, exactly what we had from the beginning. So we see that essentially this is the mass line. So starting from the original transfer function, starting from g of s here, substituting j omega, so we have g of j omega, and then we have these low frequency approximations. We find that g of j omega looks like a spring, and at the high frequency approximation, it looks like a mass. Okay, so I'm going to start on a new topic now, and this is actually material that starts in section 10.7. This has to do with using the Bode plot to analyze the stability of a closed loop system. And so I've got an equation written down here. So the idea is that if we have a block diagram that looks like this, which I want to use black for this, we have a feedback system with some transfer function L of S. Okay, we have negative feedback here. So L of S here is what I'm calling the loop transfer function. Okay, so L of S is all the transfer functions that are inside this feedback loop multiplied together. When we did the root locus, we called this F of S. I'm just using a different terminology here because this is consistent with what the book uses. And the idea is that for this system to be stable, closed loop, I'll call it bounded input, bounded output, stability. We require that the gain of the loop transfer function be less than 1 when the phase of the loop transfer function is equal to minus 180 degrees. So let me motivate this just a little bit. Some intuition. Okay, so if you remember now, all these feedback loops we've been using, we always use negative feedback. That's why there's this little minus sign like this. Let's suppose that we had something where we have positive feedback. Okay, and I'm just going to call this A. So A is some amplification. It's a number, right? Okay, so let's say we have positive feedback. Okay, so if we have a positive feedback system like this, it turns out it's only stable if A is less than 1, okay? And intuitively what's going on is we take a signal, we feed it into this loop, we multiply by A, and if that value is more than 1, what we're doing is we're taking that thing that is bigger than our input and we're feeding it back around. And so each time we go around the loop, we multiply by A, and we multiply by A, and we multiply by A. And so each multiplication makes the signal bigger and bigger and bigger and bigger. And so intuitively, we can kind of understand that what happens is that that output will grow without bound, right? Because we're going around the loop, and each time we go around, we're making the signal bigger and bigger and bigger, okay? However, if A is less than 1, then what we're doing is we're making the signal smaller. We're coming around again, we're multiplying by A again, so we have A squared, and that's a number that's also less than 1. It's even smaller. And so the signal gets smaller and smaller and smaller and smaller. And so if we think about like kind of a convergent series, you can imagine that that will converge to some constant value, right? So this is true. Our intuition is right. It turns out that a positive feedback system is only stable if the gain around the loop is less than 1. Okay? Negative feedback systems actually can be stable if this gain A is bigger than 1. Okay. So now how does this connect to our diagram up here? Well, okay, here's our loop transfer function. And let's imagine, right, we have all these things, we plotted things that have Bode plots. So let's imagine that we're putting in a particular frequency here, right? So we have like u of t is sine omega t, so we're forcing at some frequency omega. So the phase of this transfer function, right, we could find by evaluating L of j omega at the particular frequency. And there are, depending on how many poles and zeros of the systems, there's going to be some frequencies where this L of j omega has minus 180 degrees of phase shift. Okay. Well, if you remember, so going back to this discussion about the second order system, let's look at the very beginning here where we're talking about the mass spring damper. Okay, so y is equal to minus something times sine omega t. So minus 180 degree phase shift means that we're taking a positive force and we're getting a negative output. Okay, so basically what's happening is that if you think about the loop, it is becoming inverting. It's taking a positive signal and it's inverting the sign. It's making it a negative sign. Okay, so what does that mean in the context of the feedback loop? Well, what it means is that if we're at a frequency where this transfer function is inverting, it's like we're going through here, we got a minus something, we're coming back around, we multiply by minus again, and so what is that? Well, we have two negative signs, they become a positive sign. So the loop is actually a positive feedback loop at the frequencies where the loop transfer function has minus 180 degree phase shift. And so what we have to do is to ensure stability is that when this loop transfer function has minus 180 degree phase shift, it better be simultaneously that the gain of the loop transfer function is less than 1. Okay, and then we can ensure that we go back to this positive feedback loop, we can ensure that A, the gain of the loop, is less than 1, and so it's going to be a positive feedback system that is a stable positive feedback system. Okay, so how do we use this? Well, the first thing is we're going to define a couple of parameters. I actually will define them briefly, and then I'm going to show a picture and explain what they are. These are two margins. One is called the gain margin. It's the gain increase required to make the system unstable. The phase margin is the phase shift increase required to make the system unstable. And these are like margin of safety, right? So we have, you probably know from your design classes, we design some margin of safety, typically, for example, like on a fracture stress or something. We design the part so that the maximum stress that it sees is maybe half the fracture stress or maybe a third of that, and that gives us some margin of safety. Same idea here. So the idea is that we want to make sure that we can actually, the gain could increase by a lot in our system before the system goes unstable. Okay, so let's say, for example, we have a gain margin of 20 dBs. That means that the system is stable, and we'd have to increase the gain by 20 dB or a factor of 10 to make it go unstable. And in all likelihood, it's very unlikely that we'd ever have a system that would see somehow some factor of 10 change in the gain over the service life of that system. So these are designed to be basically margins of safety. And let me illustrate them here graphically. This is a plot again from chapter 10. It's figure 10.37, and it shows the gain and the phase margin on a Bode plot. Okay, so the plot that's at the top here is the magnitude plotted in decibels. Okay, and they're not showing here the whole magnitude response. Okay, so the magnitude response may be flat, it may go up, it may do some things here, but we don't care about any of that stuff. What we really care about is where the gain plot crosses through 0 dB. Okay, because if we sort of look over here, we could see that the gain is more than 1. So for frequencies in this range, the gain is greater than 1, right, which is saying it's greater than 0 dB, okay? So at frequencies below this point, the gain is greater than 1, and at frequencies above this critical frequency, the gain is less than 1 or less than 0 dB. Okay? So this is a critical frequency, and we call this the gain crossover frequency, omega CG. So it's where the gain plot crosses over 0 dBs, the gain crossover frequency. Okay? Now if we come down here and we look at the phase plot for the same system, so remember these are, let me draw it like here, this is the gain of the loop transfer function, and this is the phase of the loop transfer function. Okay? So if we look down here, here's the phase plot, and the critical point here is minus 180 degrees. So now what we're going to do is we're going to look at the gain crossover frequency. We drop down to the phase plot, and we see that the phase has not yet crossed through minus 180 degrees. So what we know is everywhere that the loop transfer function has a gain greater than 1, the phase is not yet inverting, okay, because the phase plot has not yet crossed through minus 180 degrees. And the difference between the actual phase and minus 180 degrees is the phase margin, right? And so if we look at this picture here, maybe this is 30 degrees, meaning that the phase is at minus 150 degrees at the gain crossover frequency, okay? So we could, somehow, something could go wrong with our system that would add some additional phase lag, and as long as that additional phase lag isn't 30 degrees at this crossover frequency, the system will be stable, okay? The other part of that, I mentioned, there is the gain margin. So now we're going to look over here, and we have the phase crossover frequency. That's where the phase curve crosses through minus 180 degrees, and we draw a line up to the gain plot, and we see that the gain is below 0 dBs, and so the distance between 0 dB and the actual gain is the gain margin. Okay, that's the amount that the gain would have to be increased by to drive the system unstable. So we could, let's say this is minus 20 dB here, then we could increase the gain by up to, but not exactly 20 dB, and we would make sure that the system would be stable. Okay, so how are we going to use this? Well, if we look back at this feedback system, we can take the loop transfer function, which remember is the open loop transfer function of the system, and we can make a Bode plot for it. And then based on that open loop Bode plot, we can actually determine something about the stability of the system. And this is actually just as useful, or maybe even more useful, than the root locus as a means for determining stability of the system.